You type 7 characters in your Rust code base. Just, you know, .clone parenthesis. And it compiles. The bar checker's perfectly happy. But under the hood,
Yeah.
in the fraction of a millisecond your program just ran, it silently burned through 2 megabytes of heap memory.
Yeah, it's just completely instantly.
Exactly. It triggered a cascade of cache misses. It stalled your CPU pipeline. And, well, we always hear about Rust's zero-cost abstractions, right? It's absolute engineering
That's
safety.
the big selling point, yeah.
But there's a hidden side to that promise,
Mm-hmm.
a sort of invisible tax, I guess you could call it.
Absolutely.
So today, we're diving into a 2026 presentation by a developer at Lux036. It's called Rust Memory Optimization, Surgical Precision for Leaner Libraries. And we are going to explore the really fascinating, sometimes contradictory trade-offs developers make every day between speed, safety, and, well, memory footprint.
It's honestly a phenomenal look at what happens when you stop taking the compiler's default behaviors for granted. Because, I mean, Rust's defaults heavily prioritize correctness. They want to avoid undefined behavior at all costs, but they do not automatically minimize your memory footprint.
So safe doesn't always mean lean.
Exactly. As the author points out, zero cost does not mean zero memory. When you actually start profiling the heap, you realize just how much invisible bloat is necessary just to keep those safety guarantees intact.
Which is exactly what we want to dissect for you today in this deep dive. If you've spent any time working with systems programming, you know the basic structures. But before we get into the surgical fixes the author applied to these libraries,
Yeah,
we really need to look at the mechanics of this hidden tax.
we do. Yeah.
Like, why does memory silently pile up when a developer just relies on the standard library?
Well, it really comes down to the underlying mechanics of dynamic growth and load factors.
Okay.
So consider what happens when you push elements to a vector, a vec. When it hits its capacity, it doesn't just ask the allocator for enough space for one more element.
Because that would be too slow, right?
Right, making a system call to the memory allocator is really expensive. So to
Yeah.
amortize that cost, the standard library overallocates. It usually just doubles the capacity.
Okay, let's unpack this because that makes sense for speed, right?
Right.
It's essentially like moving into a new house.
Sure.
And instead of building a new room every single time you buy a chair, you buy a house with 3 extra empty rooms just in case you have to buy more furniture later.
That's a great way to think about it.
Like, you avoid the stress and time of moving again, but you have all this wasted square footage.
Yeah, and taking that analogy further, you aren't just paying for empty rooms, you're actually paying a penalty in how you navigate the house.
Wait, really?
Yeah, and it gets way more pronounced with associative structures, like a hash map. By its mathematical nature, it requires empty space to function efficiently.
Oh, right, to avoid collisions.
Exactly. To maintain its lightning-fast lookup times and prevent hash collisions, a Rust hash map enforces a maximum load factor. It inherently leaves roughly 20% of its allocated capacity completely empty
Just by design.
by design, because if you pack it too tightly, the collision rate skyrockets. And your lookup time just degrades significantly because the CPU has to probe through subsequent slots to find your data.
So the empty space isn't an accident at all. It's a structural requirement for speed.
Precisely.
But this is where that .clone trap I mentioned earlier comes in, isn't it?
Yeah.
The presentation points out that calling clone on a hash map with 100,000 entries is it's devastating.
Oh, it's brutal. Because it's not a simple memory copy. When you clone a hash map, you aren't just doing a block transfer of raw bytes.
You're doing all the math again.
You're allocating a massive new chunk of heap memory, complete with its own 20% of empty buffer space, and often rehashing or repositioning elements to maintain the internal invariance of the new map.
Wow.
It is a really heavy, intensive operation. But because the syntax is literally just one word .clone, it feels lightweight to the person typing it. It totally bypasses our instinct for performance cost.
So we have what the source is called the Rust advantage versus the Rust tax. The advantage is unparalleled, right? No garbage collector randomly freezing your application to clean up memory, move semantics that just gracefully handle ownership.
Precise control over when things drop.
Exactly. But the tax is all these hidden heap copies and wasted overhead capacities if you just let the standard library make all the decisions for you.
And the hardware implications of this tax are what really matter. I mean, people might ask, why should you care if a background process wastes a few megabytes? We all have gigabytes of RAM in our machines today.
Sure, memory is cheap.
But it's not about the total capacity of your RAM sticks. It is about the CPU cache.
Ah, right. L1 and L2 cache.
Yes. The CPU has these tiny, ultra fast cache lines right on the die. If your data structures are bloated with empty slots, padding, and duplicated data, the CPU just can't fit as much useful information into that fast cache.
So it misses,
It gets a cache miss and has to go all the way out to the main system RAM to fetch the data.
which in CPU time is like it's like walking to another city to get a file.
It really is. So speed and memory aren't just related. They are physically bound together by the hardware architecture. Every single byte saved means denser data, fewer cache misses, and faster code.
That makes total sense. So how do we actually fix it? Let's dive into the first conceptual optimization pattern we pulled from these case studies. Tearing out the unconscious cloning of data.
Yeah, the sources highlight several libraries dealing with heavy simulations where this was the primary bottleneck.
Like the Wolves one.
Right, the low discrepancy sequence library used for mathematical generation. The underlying problem there was just structural duplication.
What were they duplicating?
Well, every single time a new sequence generator was instantiated, the program was cloning an identical 300-element lookup table from a global source.
Oh, yikes.
So if you spawned 100 generators in a multi-threaded workload, you suddenly had 100 identical copies of this table sitting on the heap.
Just massive redundant duplication. So the fix here was to replace a standard VEC containing those floats with an ARC, right? An atomic reference counted slice.
Exactly. Essentially, instead of giving every generator its own copy of the table, you leave one single copy in memory and just hand out smart pointers.
But let's look at the mechanics of that trade-off, because nothing is free. What does introducing an ARC actually cost the system?
Well, you're trading heap allocation for atomic synchronization.
Okay, meaning what?
An ARC is thread safe, meaning multiple threads can look at that single table simultaneously. But to ensure memory safety so the table doesn't get dropped from memory while a thread is still reading it, the CPU has to maintain a reference count.
Right.
Every time a new generator looks at the table, it performs an atomic increment.
And an atomic operation is notoriously heavy at the hardware level, right?
It is, yeah. When one CPU core updates that atomic reference count, it
Mhm.
essentially has to lock the cache line across the motherboard bus. It forces the other cores to invalidate their cached versions of that counter.
Oh, wow. So it literally stops the other cores.
It does. That synchronization takes precious nanoseconds. It stalls the pipeline. So the developer is making a very intentional, context-aware choice here.
They're accepting a tiny bit of CPU pipeline stalling on creation to completely eliminate massive repetitive heap allocations.
Precisely.
It's kind of like having a shared map in a glass case.
Okay.
Instead of printing a new map for every single person who walks into the building, which wastes paper and time, you just have one map. But you have a security guard standing there, forcing every single person to slowly sign a logbook before they can look at it.
That captures the atomic trade-off perfectly, actually.
It creates a small bottleneck at the logbook, but you save a forest worth of paper.
Yeah, and the savings in this specific library were immense. They saved kilobytes of memory per instance and drastically improved cache locality because all the threads were hitting the exact same memory addresses.
That's awesome.
Uh-huh.
But let's flip the perspective, though. What if you're dealing with data that does change, where you can't just share a read-only table?
That brings us to the CSDR's library.
The canonical sign digit conversion one?
Right, they had a classic string building problem. Inside a really heavy conversion loop, the program was building a string buffer, and at the end of the loop, it would clone the entire thread local buffer just to hand it back to the caller.
Which is a textbook who owns the data dilemma.
Exactly. So to eradicate that final clone, the author utilized a function called std memtake. It's this brilliant function that essentially swaps ownership.
How does this hold up?
Instead of making a heap copy of the populated buffer to return to the user, memtake pulls the populated buffer out of the struct and leaves a completely empty default buffer in its place.
Ah,
You hand over the original data without copying a single byte.
I love that. I just take the full folder out of my drawer and hand it to you and put an empty folder back in my drawer.
Exactly.
But wait, if I use memtake, aren't I just shifting the allocation penalty to the next iteration of the loop? Because now my thread local store has an empty buffer. The very next time that conversion function is called, it's going to have to ask the OS allocator for brand new memory to start building the next string.
You hit the nail on the head. And this is where profiling reveals the truly hidden nature of time versus memory trade-offs. By using memtake, you are intentionally choosing to repeatedly hit the memory allocator.
So it's slower.
The old dot clone method was actually faster for tight, repetitive loops, yeah. Because it kept the original buffer at its full capacity in the background, It amortized the allocation
After the
cost.
memory footprint was worse.
Terrible. Because you kept that bloated buffer sitting around in the thread local storage forever, even when the system was completely idle.
I see. So Memtake slows down the peak throughput of a tight loop, but it guarantees that your baseline memory usage drops back to near zero when the function finishes.
Exactly. You are choosing a flatter memory profile over raw CPU speed. It forces the developer to ask, what is the actual life cycle of this application?
Right, like if it's a web server processing thousands of concurrent requests.
Keeping thousands of bloated, dormant buffers in thread local storage will just crash your server with out of memory errors.
Hmm.
The CPU hit from reallocating is the price you pay for stability.
Which directly contrasts with another approach in the sources, right? Where the developer decided to aggressively hoard memory to save time.
Ah, yes. The Algor's convex optimization solver.
Right. The algorithm was dynamically allocating 4 temporary vectors on the fly during every single cutting plane iteration.
Which is wild because if that mathematical iteration runs 10,000 times, you are triggering 40,000 individual heap allocations.
The OS hates that.
The overhead from hitting the system allocator that many times will utterly destroy your performance.
So the solution here was to pre-allocate scratch buffers.
Right. Yeah, the developer altered the core data structure to permanently contain those 4 vectors. The struct carries them around internally, clears them out after each iteration, and just reuses the exact same memory space.
Hold on, aren't we just building the empty rooms we complained about earlier?
We are.
If I inject 4 vectors into a struct permanently, I am severely bloating the size of that object in memory, even if it's currently doing nothing.
You are. The author specifically notes this structural change adds about 128 bytes of permanent overhead to every single instance of that solver.
Okay.
So if you instantiate the solver, run it exactly once, and drop it, this optimization is a massive failure. You just paid for 128 bytes of permanent baggage for a remarkably short trip.
But these solvers don't run once.
Right. They run deep algorithmic loops. For long-running objects, the amortized savings of bypassing the OS allocator 40,000 times makes that 128-byte tax completely negligible.
It's so dependent on the execution context. I mean, in the string building scenario, they gave the buffer away to save baseline memory, sacrificing loop speed.
Yes.
Here, they permanently hoard the buffers to maximize loop speed, sacrificing the baseline footprint. It just proves that the compiler's default behavior cannot know your business logic.
Absolutely. And sometimes, the problem isn't even about how you manage the allocations. It's that your foundational data structure is fundamentally the wrong tool for the hardware architecture.
Which brings us to the next section of the presentation, right? Transitioning from minimizing clones to completely rethinking core layouts, which is arguably where the most dramatic performance gains happen.
Oh, for sure. Let's look at how they tackled graph operations in a library called NetListXers. They were managing relationships between electronic modules using an index map from string to node index.
Which on paper sounds perfectly logical. You have a string representing a module's name, and you want to look up its index in the graph.
It is the most intuitive way to write the code. But when you inspect the memory profile, you realize those module strings already exist elsewhere in the application's memory space.
Oh, I see.
So by using an index map, the structure was physically duplicating every single string key just to use it for hashing.
Wow. When you scale that to 100,000 hardware modules, you're hoarding megabytes of purely duplicated text data.
Exactly. So the developer tore out the index map, they split the logic, they replaced it with an index set to track uniqueness, paired with a parallel vec of node indexes to hold the actual values.
But mathematically, doesn't that make the algorithm worse?
How so?
Well, by splitting it, a lookup now requires 2 distinct operations, right? First, you have to hash the key and probe the index set to find the position.
Right.
Then you have to take that position and execute an array access on the vec to get the index. Why would doing 2 operations be faster and leaner than doing 1?
This is where algorithmic complexity, the big O notation we all learn in computer science, collides with the physical reality of silicon hardware.
Okay.
Intuitively, yeah, 1 operation should be faster than 2. But an index map is a heavy, complex structure. It stores the keys, the values, and the metadata for insertion order all bound together. It suffers from poor cache locality because the data is spread out.
Whereas a vec.
A vec is just a contiguous block of raw memory.
So jumping to a specific index in a vec is basically instantaneous for the CPU.
Exactly. The CPU's hardware prefetcher loves dense arrays. It can load chunks of that vec into the L1 cache before your code even asks for it.
That's incredible.
So yes, you are performing two logical operations. But the second operation, the array lookup, is so physically cheap for the CPU that it easily beats the heavy pointer chasing and cache missing that the massive index map required.
You sacrifice some convenience, but the memory density improves so radically that your overall execution time drops.
Precisely.
It's like taking a bus that stops directly in front of your destination
Right.
versus taking a high-speed train that drops you 3 blocks away.
Oh, I like that.
The walk from the train station is an extra step, but the train moves so fast that your total commute is still shorter.
That physical layout dictates everything. And we see a similar structural overhaul in how they handled cycle detection in directed graphs in the digraphs extras library.
Right. The original code was dynamically creating a fresh hash map for visited nodes on every single recursive call.
And we know from earlier what initializing a hash map means.
It means allocating that 20% empty buffer space and setting up the hashing state. Doing that inside a recursive loop sounds catastrophic for memory fragmentation.
It is. So the developer applied the hoarding pattern again. They pulled the visited map out of the recursive function entirely and anchored it as a permanent field on the parent struct.
So instead of destroying and recreating it, they just clear it out after each cycle detection run.
Exactly. But just like the scratch buffers, this adds a permanent 48-byte overhead to the struct, which is the size of a hash map header.
You're paying a permanent memory tax up front to avoid an exponential allocation tax during the execution. It really requires you to know exactly how your data flows.
It does. Which brings us to perhaps the most surgical intervention in the presentation, focusing purely on algorithm selection rather than data structures.
The PhysIDs one.
Yeah.
The clock tree algorithm for physical design.
Yeah. The underlying logic required splitting a massive data set perfectly in half at every level of recursion.
And the original implementation achieved this by calling Rust's standard sort function on the entire array, right? And then just grabbing the middle element,
A full sort operation.
which is O of n log n. It has to meticulously organize every single element in the array from smallest to largest, which involves moving a lot of data around in memory.
But if you analyze the requirement of the algorithm, it doesn't actually care if the first quarter of the data is sorted. It doesn't care if the last quarter is sorted.
It just needs the middle.
It only cares about finding the exact median value to split the tree. Sorting the entire array is a massive over-execution.
So they swapped it out. They dropped the standard sort and used a function called select and unstable. This mathematically finds the median and partitions the data in O of n time, which is astronomically faster.
It is. But reading through the sources, this isn't just a free speed boost. The compiler enforces a very strict trade-off here regarding ownership and borrowing.
Right, this is a fantastic point about the ripple effects of optimization.
Yeah, to find the median in O of n time without allocating extra memory, select unstable has to physically shuffle the elements around within the existing array.
It has to mutate the layout.
Yes. This means the function signature must be changed to require a mutable reference and ampersand mut in Rust.
The borrow checker enters the chat.
Precisely. The original full sort method likely took an immutable read-only reference, made a copy, and sorted the copy. Changing that requirement to a mutable borrow completely changes the API contract of the function.
Oh man, so if any other part of your code base was holding a read-only lock on that data,
Or if downstream code implicitly relied on the array being completely ordered rather than just partitioned.
your code will instantly fail to compile, or worse, introduce logic bugs.
It's the definition of surgical precision. You are cutting away the exact inefficiency, but if you don't understand the anatomy of the entire application, the patient bleeds out on the table.
You can't just blindly swap functions.
No, you really can't. Which leads perfectly into the macro level philosophy the author presents. How do you actually achieve this? You cannot just guess where memory is leaking or where cache misses are happening.
Right, human intuition is remarkably bad at predicting hardware behavior at scale. So what did they use? The presentation lays out a very specific diagnostic toolkit.
They didn't just use standard speed benchmarks, they heavily utilized ATTORS, which is a heap allocation profiler.
So it doesn't just tell you how fast a function runs.
No, it literally traces every single time your program asks the OS for memory, pinpointing the exact line of code responsible for the bloat.
Because a standard time-based benchmark using something like Criterion might tell you a loop is fast, completely missing the fact that the loop is leaving megabytes of orphaned capacity in a thread local store.
Exactly, and that will eventually crash the system. They also utilized std memsize ifs in their testing pipelines to actively catch struct bloat.
Oh, smart. So if a developer accidentally adds too many permanent scratch buffers to a struct, the test just fails.
Right, it prevents cache line degradation from creeping into the main branch.
It's about building visibility into the invisible tags. From all of this, the author distills two critical rules for optimization. First, structural over micro.
Changing the physical layout of your data, like moving from a massive index map to a parallel vec, or replacing an O of n log n allocation with a mutable O of n partition, will always yield better results than just trying to write a slightly tighter for loop.
You have to align your data structures with the physical reality of the CPU cache before you worry about the specific instructions operating on them.
Exactly. And the second rule is fundamental: profile first.
Measure the heap, measure the cache misses, and optimize only what is actually bleeding resources. So bringing this all together, what does this mean for you navigating your own code base?
Well, even if you never compile a line of Rust, the principles we explore today dictate the behavior of everything from the database running your company's backend to the browser rendering this audio.
Software engineering is entirely a discipline of managing trade-offs. The standard library defaults in modern languages are incredible. They're designed to protect you from seg faults, prevent data races, and get your product shipped.
But they are generic. They have to be generic to be safe.
Right.
True optimization requires intentionality. It demands that you understand the life cycle of your data. Are you in a tight loop where you need to hoard memory to save CPU cycles? Or are you in a long running background process where you need to give memory back to the OS to maintain stability?
And the presentation concludes with a really staggering metric. Across 38 files and 6 different open source projects, the author achieved 0 performance regressions.
Zero. They didn't slow a single metric down.
But by strategically applying these trade-offs, swapping arcs, managing memtake, restructuring parallel arrays, they eliminated gigabytes of hidden memory tax across thousands of algorithmic runs.
Safe code can be remarkably lean code, provided you do the work to align the structures with your specific reality.
It demonstrates the power of manual contextual engineering.
It does. But, looking at the sheer amount of manual labor required to profile, diagnose, and swap these structures, it raises a really compelling question about the future of how we write software.
Like what?
Well, right now, you have to actively decide to use a dot clone here or a memtake there based on static analysis. But what if the next generation of compilers didn't rely on static defaults?
Oh, wow.
What if your language runtime could profile your software dynamically as it executes and physically restructure its own memory layouts in real time?
Imagine a system that automatically swaps a hash map for a dense vec when it detects high cache misses.
Adjusting its own trade-offs millisecond by millisecond based on the live pressure of the hardware.
A self-optimizing system that remodels the underlying architecture while the application is still running. Tearing down the empty rooms when you don't need them and building them back when you do, completely invisibly.
It's the ultimate zero-cost abstraction.
That is a wild thought to leave on. Thank you for joining us on this deep dive. Keep questioning the invisible defaults in the systems you rely on, and we will catch you next time.